Good morning and welcome to today's webinar, Debugging PCIe Interface up to 32 Gbps Gen5 Data Rate. My name is Pranav Jagdish and I'll be your host for today's session. We have two esteemed presenters with us today. First, we have Mr. Prajesh P, Senior Director of Hardware Engineering at Prodigy Technovations, with nearly 20 years of research-oriented experience in FPGA product-based development and ASIC IP design. Joining him is Mr. Vibhav Karki, Senior Engineering Manager, Software, who brings over 15 years of industry experience in system software and high-speed protocols. In this webinar, Prajesh and Vibhav will provide an overview of PCIe and NVMe protocols, explore the key features involved, and discuss the common challenges in debugging protocol layer issues. They will also introduce the Prodigy Technovations PCIe Gen5 protocol analysis solution, showcasing its key features and real-world applications. We encourage you to actively participate in the webinar by posting questions in the Q&A window throughout the session. The last 10 minutes of the webinar will be dedicated to answering all your questions. Please note that the webinar is recorded and the link for the recording will be sent to you after the webinar. So if you experience any connectivity issues, you can catch up later. Now, without further ado, I'd like to hand over to our first presenter, Prajesh. Over to you.
Good afternoon. So today we'll be discussing about PCIe and NVMe protocol and a brief overview of our protocol analyzer. So agenda for the day. So we'll have a brief introduction about Prodigy Technovations and what we do. So we'll have a overview of PCIe and NVMe protocols and a short discussion on the challenges involved in PCIe protocol analysis and the features of Prodigy's PCIe and NVMe protocol analyzer and a short demo of the protocol analyzer. So coming to Prodigy Technovations. Prodigy Technovations is a Bangalore-based technology company providing protocol analyzers and exercises for various serial communication protocols. We have mainly two product categories. First one is software application targeted to run in oscilloscope for electrical validation of the data captured at a very high sampling rate by the scope. So this solution is not meant for detailed protocol analysis because the scope generally have a limited capture depth. So this solution mainly targeted for voltage and timing parameter measurement as per the specification. The next category of product is the hardware assisted protocol exerciser and analyzer, where a dedicated custom-made hardware is used to acquire the data and do the low-level protocol analysis, while a PC software application does the higher layer protocol analysis and all the GUI features. So we have products ranging from very low speed protocols such as UART, I2C, SPI, to mid-range protocols like SPMI, RFFE, eMMC, SD, and very high-speed protocols like PCI and UFS. So do contact us for any of your protocol analyzer and exercise requirements. We are open to customization request, and we are also open to develop products for your custom protocols. So our R&D facility is located in Bangalore, and we have sales and marketing network throughout the globe through our distributors. So that's a short description about Prodigy, and coming to our today's session. So PCIe is basically a high performance serial point-to-point interconnect between two devices. So it implements a packet-based protocol for information transfer. So it supports multiple link width like X1, 1 lane, 2 lane, 4 lane, 8 lane, and 16 lane. So it used to support 32 lane, but in the recent specification that is deprecated. So it supports a lot of features like power management, hot plug and swap, data integrity and error handling. And it supports multiple interconnect use cases like chip-to-chip and board-to-board connections using PCB traces, cables, or connectors. So this is how a PCI link looks like. So since it is a point-to-point interface, you'll have a PCI link between component A and component B. And this is basically a dual simplex link. So you'll have data transfer happening in both the directions simultaneously. Along with the actual data lines, there are other signals like clock and sideband signals, which we'll be covering later. And the topology looks like this, where you basically have a root complex, which normally is a CPU. And normally there will be an integrated root complex inside the CPU itself. And the root complex connects to directly to the endpoint or through the switches. So there can be multiple levels of switches. One switch can connect to another switch and to another switch like that. So there can be a number of devices in the network. So on power on CPU will identify all the root complex will identify all the devices, and it will assign the bus device and function numbers, and it will be able to communicate to each and every device. And there can be bridges between PCIe to different protocols as well in the network. So these are the data rates supported by PCIe protocol. So Gen1 starts at 2.5 gigatrans per second. So based on the number of lanes, it can be 2.5 Gbps or 2.5 Gbps into 16, if there are 16 lanes. And Gen2 at 5, Gen3 at 8, Gen4 at 16, Gen5 at 32, Gen6 is at 64 gigatrans per second, and Gen7, which is currently under development, will be supporting 128 gigatransfer per second. In terms of signaling, up to Gen5 it supports NRC signaling, and Gen6 supports PAM4 signaling. So Gen1 and Gen2 uses 8-bit NB encoding. Gen3, 4, and 5 uses 128, 130B encoding, and Gen6 uses 1B, 1B. Scrambling is optional in Gen1 and Gen2 because 8-bit NB already takes care of the data transition requirements for the clock recovery. But in Gen3, Gen4, and Gen5, since encoding is not used, scrambling is mandatory, and even in Gen6 also. So these are the different options for connections. Root complex and endpoint are connected using different interfaces. So one of the most commonly used interfaces is M.2. So depending on the application, there are different kinds of M.2 interfaces. So you can see this opening here is called the key. So this is an M.2 M key, normally used for SSD applications. Or if you're using it for a Wi-Fi or a Bluetooth kind of interface, you'll have a different key, normally E key. And it all depends on where that gap is there in the connector. And M.2 supports X4 link. And the another interface is U.2, which is normally used for the enterprise SSDs, and it supports X4 link. And it also supports a dual port where it can operate as two X2 links. So other option is the commonly used AIC or a SEM interface, which can support up to X16. So this is a very common interface used in all the motherboards, especially to support all the add-in cards like graphics card or any other add-in cards. All the motherboards normally comes with this interface. The other option is a cabled connection where OCU link cable can be used to interface to devices. And there are other interfaces also like E1.S, E1.L, E3.S, E3.L and all, which are used in the enterprise SSD market, so which are not included in here. So those are the new kind of interfaces. Other option is like an onboard connectivity where a device which supports NVMe protocol communicates to the host, and both are on the same hardware, and it can communicate to the device, and host can communicate over the PCB trace. And in many cases, processor and FPGA are used in the system where FPGA acts as the endpoint and the processor acts as the host. So coming to the details of the PCIe protocol. So PCIe supports ISO-SA layered architecture where you have the lower layer, physical layer, which has an electrical and logical subblock, then the data link layer and the transaction layer. So the higher layer, high level packet structure looks like this, where the data, actual user data comes from the transaction layer, flows through the data link layer, physical layer, and it reaches on the other side, reaching the physical, then go to data link and transaction. So in the transaction layer, we have the transaction layer header and the data. Again, this is data depending on the kind of packet, data may or may not be there. And there is an option for having the end-to-end CRC. I'll explain it. And the data link layer, once the data flows from the transaction layer to the data link layer, it adds the sequence number to that packet, TLP packet, and it adds the link level CRC. And once it reaches the physical layer adds the framing sequence, which is basically indicating the start and end of packet. So normally the flow control or the error checking happens at the data link layer. So that is why the link level CRC is mandatory. So the data link layer makes sure that data is transferred from one device to the other device error free. And in case if any error is detected, it has the option to retransmit. But this is always on a point-to-point basis. But if the user wants to have an end-to-end CRC on the user data, there is an option to have the eCRC, but that is optional. These are the TLP types. I'm not getting into details of every commands, but most commonly used TLPs are like memory read and write request, IO read and write request, and configuration read and write request, and completion without data and completion with data. So these are directly taken from the PCI specification. So now let's see how a PCI transaction normally happens. So this is an example of a root complex to endpoint transaction where the root complex is the initiator or the requester and the endpoint is the completer. So it can happen between from root complex to any endpoint. So in this case, we considered this endpoint as the final destination. So the root complex issues a memory read command, and then the switch based on its routing table, it knows where the destination is, so it routes it to the corresponding node, which is again the next switch, and the next switch sees that it is targeted to this endpoint, and the request reaches the endpoint. Once the request reaches the endpoint processes the request, and then since it is a read request for reading the data, it responds with a completion with data packet, and that data packet again gets routed back to the root complex. So the procedure is same even if the endpoint initiates the request to read from the host memory or the root complex memory. Only thing is it starts from the endpoint and then the request reaches the root complex and the root complex returns the data. So in this whole data flow, the TLP packets moves from the root complex to the endpoint. But since the PCI is a point-to-point link, the acknowledgement and the data correctness test happens between point-to-point. So first, when the root complex issues a read command to the switch, that is one link. It's a point-to-point link between the root complex and the switch. So the acknowledgement or NAC for that particular transaction happens between the root complex and the switch. And in case if the request is not processed, root complex retains that request and it can retry it till it is acknowledged. So that is, so for every link, first is between the root complex and the switch A, then switch A to switch B and switch B to endpoint. Those are all point-to-point link, and the data link layer mechanisms like acknowledgement and the flow control happens between these things. Now this is another example of a peer-to-peer transaction where endpoint connected on one switch network talks to another one. So here, since these are not directly connected, it's connected to the root complex. Whatever request initiated from the endpoint, it gets routed through the root complex to the next endpoint, and the endpoint returns back the data. So all kind of scenarios are possible based on where the endpoint sits in the entire network. Now coming to the data link layer, it is an intermediate stage between physical and transaction layer. So its main responsibility is to provide reliable mechanism for exchanging the TLPs. So as I mentioned, it generates the LCRC and inserts it to the TLP. It generates the sequence number for tracking the TLPs and to do retransmission in case the TLPs are not received correctly. And also it controls the flow control by exchanging flow control credit. So I think we'll come to that later when I explain that packet. And also it gives the acknowledgement and NAC for all the transactions, and it conveys the power management states also, and it has the error indication and reporting functionality. So these are the data link layer packets. So it's a 6-byte fixed packet structure where the first byte indicates what type of data link layer packet it is, and the remaining fields depends on the type, and the last 2 bytes are the CRC for that DLLP. So main packets are like these PM packets are mainly for the power management, basically to enter the low power and low power states. And these FCs are the flow control packets, basically the init FCs and update FCs. So init FCs are transmitted at the beginning of the transfer or on power on during the initial phase, and then update FCs are transmitted frequently. So there will be a flow control packet for all different types of packets like non-posted, completion, and posted packets. So these flow control packets are basically used to indicate how much buffer size is available in the device. So PCI works on the credit-based mechanism where the initiator will look for the flow control packet and understand how much buffer space is available on the other side, and it would initiate the transfer in such a way that the data whatever is transferred will can be received by the other side. Just to make sure that buffer is available. This is just to make sure that link is used very efficiently. Yeah, now coming to the physical layer, filer basically does the encoding and the framing. So for Gen 1 and Gen 2, it uses 8-bit NB encoding. So these are the basic control characters which are used for framing purpose. So you have this start TLP, start DLLP, and embed kind of control packets which are used for the framing, and there are other control packets symbols like skip which are used for the clock synchronization, and FTS is used for entry and exiting from the L0 state. Since Gen 3 and Gen 4 doesn't use 8-bit NB encoding, so it doesn't have a dedicated control symbol to indicate the start and end. So it uses basically the framing sequence. So these are the framing sequence used by Gen 3, Gen 4, Gen 5. Idles are basically the logical idle are zeros, but it will be on the line. You will still see scrambled data, so it won't appear as zero on the line. It will be all scrambled. And SDP is for the start of DLLP, STP is for the start of TLP, and embed. Embed is for indicating the null packet where say the host or device is sending a packet and then it is not valid anymore. And end of data stream is to switch from the control packets to the data. Now PHY has something called ordered sets. So these are like physical layer packets consisting of a series of symbols. These are always transmitted serially on each lane such that the full ordered sets appears on each lane. These are mainly used for the initial link training, and some sequences like skip are transmitted on a regular interval for the clock tolerance compensation. And when the link needs to be placed into low power states, even for that the ordered sets are used. So Gen 1, Gen 2 ordered set, since it uses 8-bit NB, it has a special skip symbol as part of the 8-bit NB control character. So it transmits the COM character followed by the COM character followed by the OS ordered set packet. And Gen 3, Gen 4 ordered set consists of a sync header followed by full sequence of ordered sets symbols. And not getting into the details of ordered sets, it is well defined in the spec what each symbol consists of. Ordered set are always like 128-bit in length. So these are the different types of ordered sets. Skip ordered sets which are used for the clock correction and clock compensation, skip and control skip. So in Gen 4 and Gen 5, skip and control skips are transferred alternately. Electrical idle ordered set and electrical idle exit ordered sets and fast training sequence ordered sets are used for low power entry and exit. Training sequence 1 and training sequence 2 are used for initial link training, and start of data stream is used to switch between the control data and the actual control and data. So now let us see the LTSSM. So this is a link training and status state machine. This is basically used initially to establish the link. So on power on, all the devices goes through this link LTSSM states. So whoever comes first, it starts with the detect state. So detect is basically to detect if the other end is the other side is connected or not. So it is basically determined using the parent termination detection. And then is the polling state. In polling state, devices start sending the training sequence 1 and 2. This state is used to achieve bit and symbol lock. So basically, it will be a repeated kind of pattern, so which makes sure that enough transitions are there. So the receiver side CDR can lock to the data and it can achieve a bit level and symbol level lock. And each state has multiple substates, which is not captured here. So almost all states have 3 to 4 substates, which you can see in the spec. So after polling, it goes to the configuration state. This is a state where the link is actually established. So depending on the common link width, both the side of the link will agree to a common link width. Say assume that the root one side is supporting X4 and the other side is supporting X2. It will finally agree for X2 link. So here the link number and the lane number will be decided. So the link physical link number and the logical link number can be different. So if you have physically 0 to 4 link, so the actual logical link can be 3 down to 0. So that's why it establishes the link width and the lane number so that both sides knows which link is first link and which lane in the link is the first one. So there can be multiple links as well. So if both supports X4, it can operate in 1 link of X4 width, or it can operate in 2 links of X2 or 4 links of X1. So all those combinations, whatever is supported in the spec is possible. So all that is established during the configuration state. And once the configuration is done, it goes to the L0 state, which is the normal operating state where all the data transfer happens. And and any other state, like if the speed change or if any low power entry exit, it all happens from the L0 state. L0S is the low power state, which is minimal low power, where it can directly come back to L0 using the fast training sequence. L1 is a deep low power where it has to go to recovery, and L2 is the L2. Once it goes to L2, it has to again reinitialize the link. So coming to recovery state is used basically during all the link speed changes or for any low power L1 to L0 re-entry. So normally when any device starts, irrespective of whether it supports Gen 3, Gen 4 or Gen 5, all the devices starts from Gen 1 speed. So it will be in dictate state, polling state and configuration, and it comes to L0 at Gen 1 speed. Now assume that both the devices supports Gen 3. Once it reaches L0, it goes to recovery state and then it changes the speed. Both the sides changes the speed. Since Gen 3 needs receiver equalization, it performs all the receiver equalization in the recovery substates. And once it achieves required bit error rate, then it comes back to L0 at Gen 3 speed. Now, if Gen 4 is supported by both, then the sequence is Gen 1 dictate polling configuration, Gen 1 L0, then it goes to recovery, change speed to Gen 3, do the equalization, come back to Gen 3 L0, then again it switches to recovery, change the speed to Gen 4, do the Gen 4 equalization and comes back to Gen 4 L0. For Gen 5, it is the same. Gen 1 L0, Gen 1 L0, Gen 1 recovery, change the speed to Gen 3, then come back to Gen 3 L0, then Gen 3 recovery, then change the speed to Gen 4 equalization, Gen 4 L0, then again switching back to recovery to change the speed to Gen 5, then Gen 5 equalization and come back to Gen 5 L0. But in Gen 5 specification, there is an option to skip the equalization. which was not available till Gen 4. So there are two options. One is you can skip the intermediate stages of equalization. So once you reach Gen 1 L0, it can go to recovery and directly change the speed to Gen 5 and do Gen 5 equalization and then come back to Gen 5 L0. The other option, this is useful in case you are sure about how much equalization is required, and so that you can avoid all the intermediate stages and do, save the time for all the initial equalization stages of Gen 3 and Gen 4. The third option is to completely skip the equalization process. So this will be mostly useful in a fixed system where both the devices knows what the transmitter and receiver characteristics of the devices are, so that the equalization settings can be pre-programmed. So in this case, it can directly go to Gen 1 L0 and then go to Gen 5 speed, and without performing the equalization, it can come back to Gen 5 L0. So this is a brief overview. There are a lot of options and branches possible here. So I'm not getting into all that since we have very limited time for this webinar. And along with the normal data signals, there are a lot of sideband signals, and sideband signals are different for each interface. So M.2 may have a specific set of sideband signal, but U.2 and other interfaces will have a different set. So these are very common sideband signals. First one is the reset, and then the other things is like clock request and wake, and then there will be something like an SMBus protocol, which are mainly used for any temperature or power related readings if the host wants to read, or if you want to do a management protocol over the SMBus, that's also possible. So reset on power on, once the power level goes to the desired level, the clock request is removed, then the clock starts, and when the reference clock is stable, the host will remove the reset, and this is where the LTSSM starts. And clock request is normally used for dynamic power control, where either side can request for a low power entry. So basically the clock request will be deasserted, and then the clock can be switched off. You can still have the clock. That's like an optional feature if the device of the either side wants to save more power. Reference clock can be switched off, and once the clock request is again asserted again, it has to restart the clock. So it goes to the L1 state, which is low power state, L1 entry, L1 idle, and then comes back to recovery, and then it goes to the idle state. Now coming to NVMe, PCI is very generic protocol, so it doesn't have really any mechanism for queuing the commands and all. So NVMe is a scalable host controller interface designed to address the requirement of the SSDs basically. So it supports optimized command submission and completion paths. Basically, it supports up to 64K IO queues with up to 64K outstanding commands per queue. So you can queue your commands so that the other side can fetch the command and execute it, so that the involvement of the root complex or the processor can be minimized. And yeah, so it supports a lot of features like priority, basically weighted round robin priority with options for high priority transactions. And most all these PCI supports up to 4 kilobyte read request. So basically all the information needed to perform this 4 kilobyte read request is included in the 64 byte NVMe command. So NVMe command is fixed at 64 byte, and it has all the information to transfer a 4 kilobyte data. So it supports like multiple namespaces. Namespace is basically a quantity of a non-volatile memory that may be formatted into logical base. Basically like a formatted memory space in the SSD. So it can have multiple namespaces, and each one NVMe controller is associated with a single PCI function. I think that will be clear from the next slide. So these are the different options possible. So as you can see here, for each PCI function, there will be an NVMe Express controller. So in the first case, there is one PCI port and one function and one NVMe controller, and there can be multiple namespaces. It's like different blocks of memory space in the device. So each namespace will have its own namespace ID. And this second one is the case where you have one port, but PCI allows multiple functions over one port. So here there are two functions, and each function has an NVMe controller associated with it. And here you can see some namespaces are shareable between two functions, and some namespaces are dedicated for each function. So all these different combinations are possible. And the third one is a case where you have multiple ports. You have two ports for each having its own functions and its own NVMe controller, and with different namespaces. So all these combinations are possible depending on the use case. So coming to the actual NVMe operation. So like I said, NVMe is based on queuing the commands. So there will be a submission queue and then completion queue. So submission queue is a circular buffer with a fixed slot size that the host software uses to submit the commands for execution by the controller. So here you can see in this figure, you have the host here and you have the different functions like controller management functionality and multiple cores. So each cores have IO submission queue and a completion queue. So this the host software updates the I think I'll come to this procedure in the next slide. It will be clear. And there will be submission queue for submitting the commands. And once the command is submitted, the controller fetches the command, executes the command, and it gives the completion status in the completion queue. And the submission and completion queue can have one-to-one mapping, or it can have an end-to-end mapping. So first case is where each submission queue has its own completion queue. And the second case is where core A's submission queue has its own completion queue, but core B has multiple submission queue and one completion queue. So all these are possible. So in NVMe, normally the controller sits in the device. So if you have an SSD, the NVMe controller will sit inside the SSD, and host will create the submission queue and completion queue in its host memory. There is an option even to create the queues in the controller memory in case the controller has enough space. Basically the RAM kind of space, then it can create. But by default, the host creates all the commands or the queues inside the host memory. So this is the procedure. So first, host writes the command to the submission queue. So say if you want to do a file transfer, it may be like a transfer from a C drive to a D drive. So it creates all those commands to transfer the data, and it creates all those commands in the submission queue. So it enters all this, each command is 64 byte. It will have the information related to how much data to be transferred from where to where. So those commands are queued in the submission queue. And once the host queues the commands, can be one command or maybe multiple commands, it writes to the submission queue doorbell of the controller. So submission queue tail doorbell is something like you queued the command and then you're just going and ringing a bell saying that I have queued few commands, so please process it. So once the controller sees a entry to the submission queue tail doorbell, so controller fetches the command. So basically this fetch is basically to read the command from the host memory. So you will see a PCIe TLP read commands going from the controller to the host memory space, reading the commands from the host submission queue, and then controller executes the command. Then once the command is executed, the corresponding status is returned to the completion queue. So you will see basically a write command to this completion queue. And once the completion queue is written, the controller generates an MSA interrupt, basically MSA signaling interrupt. And then once the host receives the interrupt, it reads the completion entry. It understands that, okay, this particular command is completed, and it writes to the completion queue head doorbell saying that the controller can free up that queue space. So this is the whole transfer. So in this, you will see a normal PCI transfer to fetch the commands, and then the NVMe read and write commands to actually do the data transfer. So this is how all the NVMe is mapped. So this is basically the PCI's normal configuration register space. So I'm just highlighted the main registers here. So basically you have the So you have the base address register, bar registers, which points to the starting address of the controller registers. So coming to the control register, so it starts from the bar register in the configuration space of the PCA, and the controller will have all these registers, and these are the offset, like start address is the offset from the base address. So main registers, if you can see, there is something called admin submission queue base address and admin completion queue base address. So basically this points to the admin queues. Okay, so there are two different kind of queues. One is like admin queue and then the IO queue. Admin queues are basically used for giving the admin commands. So admin commands are basically to say to create a queue and delete a queue, those kind of commands. So those queues, where is that admin command queue is created? So this shows that base address, and then from the base at 100H offset is the submission queues tail doorbell. First one is for the admin queue, and then remaining based on how many queues you want to create, there will be a submission and completion queue tail and head doorbell for each queue. And these are the admin commands. So basically the admin commands are all queued in the admin command queue. So these are basically used for creating the IO submission and completion queues and deleting the queues, and maybe to initially read the features of the NVMe device, set some features, and all those admin related activities basically. And these are the normal NVMe commands. So basic commands are like read, write, and flush kind of commands. So you mostly see read and write commands when you do a file transfer. Now coming to the challenges, what are the challenges in PCIe and NVMe protocol analysis? So first thing is interposers. So PCIe supports a lot of different options to connect. So you have M.2, U.2, CEM, and E1.S, E3.S, E1.L, E3. So a lot of different kind of connectors, and there can be multiple levels of switches also in the network. So designing a proper interposer to tap the data and then get it to the PA so that the PA can decode it without any errors. That is one major challenge here. And PCI uses spread spectrum clocking. So basically spread spectrum clocking is used to reduce the EMI EMC effect, so that you kind of vary the frequency at which the data is transferred. So reference clock changes from say 100 megahertz to 99.5 megahertz and goes back to 100 in a sawtooth waveform kind of pattern. And the same is reflected in the data rate. So basically, if you are at 32 Gbps, so the data rate constantly changes from say 32 Gbps and reduces to 5% of, and goes to 99.5% of that, again comes back to 32.5, like that. So because of this, we need to track the clock. We can't work completely asynchronously, so we need to have the access to the reference clock. So we use the main reference clock as the reference to our PA. And the next is the storage requirements. Since it supports very high data rate and multiple lanes, so if you are at Gen5 speed and if you support 4 lanes, it's like in one direction itself it is 128 Gbps data. So if it is 16, so it is again multiplied by 4. So and again it can happen in both the direction at the same time. So this needs a lot of storage requirements, because we can't process the data at the same rate as it is transferred on the interface. So we need enough storage on the hardware to buffer the data and then later process it in the software. So this is another major bottleneck. And the processing power, since the data rate is too high, it should be processed at a very high rate. And that is where all these parallel processing capabilities of FPGA kind of devices come into picture. And most of the customers use trigger options, so we need a real-time hardware trigger kind of implementation. So again, you need to decode the data real time, so it needs a very high-end processing platform. So these are the basic challenges involved with this kind of a very high-speed protocol analysis. Now coming to the our Prodigy's PCIe Gen 3, 4, 5 protocol analyzer. So on the right, you can see this is our protocol analyzer, and the second one is the picture which shows how the PA is connected in an M.2 system. So you basically have the root complex, and then you connect the interposer. I think I'll come to this in the next slide. So coming to the features, our PA supports Gen 1, 2, 3, 4, 5, X4 and X8. As of now, we have up to Gen 5 X4 device ready to order, and X8 will be available shortly. You can place the pre-order. And we support different kind of interfaces like M.2, U.2, CM, E1.S, SD Express up to Gen 5 speed. And it supports NVMe protocol decode. And we have optional solder down probe support up to Gen 3 speed. And our PA decodes all packets like TS1, TS2, TLP, DLLPs. Has a hardware-based protocol packet filter capabilities for idle, filtering out idles and TS1s and TS2s. It supports software-based search, filter and filter out capabilities, and supports hardware-based protocol-aware trigger capabilities for TS1, TS2, TLP, DLLP packets. And we support multi-level if then else kind of triggering capabilities. By default, we support 16 GB, and again, it depends on whether it is Gen 3, Gen 4, or Gen 5, and can be expanded up to 64 GB or 128 GB for both TX and RX. So we have a deep buffer, and we give a detailed view of all the TLPs and DLPs, and it does the LTSM analysis. We show a detailed substate view of the LTS system with all the timestamps. And there are other features like memory segmentation which are under development. And it supports a trigger out feature, which is again combined with the hardware protocol aware trigger, where you can get a signal out of the PA, which can be used to synchronize with other test and measurement equipments if required. We use USB 3.2 interface, and since we have a debuffer, and we are okay with this kind of interface. And yeah, we have options, a lot of software options. Anyway, that will be covered during our demo. We can export the result to a test file and all that. And this is a very lightweight protocol product. If you compare with any of our competitor products, it's very lightweight and it's very compact in size. And this is completely field upgradable, so you can license for Gen 4 and then later get the Gen 5 license, and it can work as a Gen 5 analyzer. Yeah, so this is coming to the system diagram. So for normal interposer based setup, we will have an interposer in between the host and root complex. So interposer can be different type based on the kind of interface what it is, and we have the solder down probe option for up to Gen 3 speed. So this is how the M.2 setup looks like. So in this diagram, you can see the PC, which is the host computer, where we have connected our M.2 interposer, and then from the M.2 interposer, all the PCI signals are coming to the PA, and the PA is connected to the PC, where it runs the PCIe software. And we have this connection, where this connection is shown here. So on the motherboard M.2 slot, we have inserted an adapter card, so which actually types all the PCI signals, and from there it comes to the interposer and it goes to the PA. And this is the setup for other interfaces like CM. So this is our CM interposer, and this is our U.2 interposer. So now we will have a demo. So my colleague Vibha will be explaining all the features of the product. Thank you.
Thank you, Prajesh. So, good afternoon, everyone. So now I'll just explain the Prodigy PCI protocol analyzer software along with its features and how it is can easily used for debugging any PCIe trace. Let me share my screen. Okay, so this is the Prodigy PCI analyzer. So there are different views here. As you can see, you have the LTSSM view, there's the main result view. So now I'm going to run a PCIe trace, which shows the decoding of the PCIe traffic along with the LT system. So as you can see, the LT system states are updated in real time. Now, to go through all the views, let me start from the left. The first thing is you have the connect. You have the connect to establish the connection with the hardware. Next, you have the acquire button to start the capture of the signals from the duty. Now, in the software, you have the setup view where you can, let me expand this. So you have various options in the setup view. So the first option is whether you want to capture from the link initialization. This is important so that you can get all the details of the configuration registers and other PCI traffic details which will be required for NVMe command decoding. If not, you have a second option to capture after link initialization. Once you choose to capture after link initialization, the initial settings will need to be entered, whether the current DUT is in Gen 3, Gen 4, or Gen 5, what's the link width, and whether there's any lane reversal. There's an option to refresh NVMe. So what this option does, so let us say you have captured from link initialization. All the bar 0 address and other details that are required for NVMe are stored by the software so that the next time if you capture a trace, the same details are automatically taken into by the software. The second option is to where you do like to share the trace file, the location of where you log to say the trace file so that it can be used for later on offline viewing. The third is the clock configuration, whether you are using a clock or an internal clock. Next, as Prajesh explained, the trigger, we support both trigger in and trigger out feature in the protocol analyzer. The next option is the enabling of the circular buffer. So the protocol analyzer has a standard memory and it also has the option for the memory to be upgraded based on the license. Now, let us say someone would like to use the circular buffer. The circular buffer means if I choose any buffer of, let's say, 8 GB, then only the last 8 GB of the traffic is analyzed and captured and analyzed by the protocol analyzer. This is mainly useful for debugging any error issues in the PCIe traffic, which needs to be run for a long time, maybe overnight, so that you can configure your DUT such that only the last, when the error occurs, you can set a trigger and the last 8 GB of the traffic can be analyzed. Along with the circular buffer, you can set a pre-trigger and a post-trigger option. So the pre-trigger tells how much of when this is automatically enabled when you set a trigger function in the protocol analyzer. So it is similar to oscilloscope pre-trigger and post-trigger functionality where you can set how much of data before the trigger needs to be captured and how much of data after the trigger. Next is the polarity configuration. By default, we keep it in auto. The protocol analyzer automatically detects the polarity and decodes the data. Next, you can also choose for the manual option where you would like to, if the physical and the actual lanes are interchanged. After that is we support various types of interposers like the M.2, U.2 and the sum interface. So these settings need to be done before the capture of the traffic. So next is the result view. The result view is where the protocol traffic is displayed on the UI. So this is the main result view. And below that is the frame view. That is each packet along with its details as enabled in the specification, is displayed for easy convenience of the user. The right side is the LTSSM view, where it shows the real-time LTSSM decoding of both the upstream and also the downstream. So the real-time LTSSM decoding, along with the number of times that each state has entered and the direction, the count of each direction from the state change is also shown. Now, this is the high-level state diagram. To go into the details of the substates, you have for both the details of the substate for each upstream and also the downstream, along with the timestamp. So the timestamp value of the substate change, along with the delta t, that's the time difference between the current state and the previous state, is shown for both upstream and the downstream. Now, let me explain all of these windows in detail. Now, the setup is a run result. We also do provide the CTLE equalization. So this is mainly, if you, let me just expand this. So this is what the CTLE, by default, our protocol analyzer in most cases works on the automatic or auto CTLE settings, and there is no need to change. But in case there is a lot of noise on the line and something needs to be changed, then the provision has been provided to adjust each and every CTLE settings on the PA. You can change or modify any of the settings easily. So you have the option to also save the current settings or load the current and restore it to its default values. Next is the trigger view. So we offer different types of trigger. One is the simple trigger. In the simple trigger, you just need to choose on which packet it needs to trigger, whether it's a TLP, DLP. So on any TLP or on any DLP or anything, the protocol analyzer will trigger. You also have the option to choose which lane, whether you need to trigger on Gen 3, Gen 4, Gen 5. And if it is you've chosen any TLP on a specific type of TLP, let's say configuration read 0. If you have chosen DLP, then any type of DLP. These can be triggered here. Next is the frame trigger. So in the frame trigger, you can trigger on the packet content. So let us say you would like to trigger on a TLP. So as you can see, this is the configuration read 0 TLP packet content. All the fields that are marked with the X, those are editable. So you can enter the value. So the frame trigger is mainly to of these contents that are marked with X to any given value, and the same will be applied for the trigger. Anything that is left with X will take it as any default value such that it triggers on any value. So you can trigger on various different types of packets and in the frame trigger. Along with this, you do have the sideband trigger where you can trigger on any sideband signals. Next is the advanced trigger. The advanced trigger is nothing where you can trigger on multiple levels. You can trigger up to 4 levels with the else condition. So as we all know the multiple trigger, you can choose for level 0 what are the conditions, then if, else, and if. So the user has many choice to trigger on any given data or packet content along with multiple packet content. Okay, going back to the result view. So the result view provides many features for ease of debugging. So in the menu, you have different features where you can just at a click of a button, you can go to the next data rate where the data rate has changed. So from the Gen 1 to the Gen 3, next you can choose whether you would like to go to the next data rate where it has changed to the 16 Gbps, the Gen 4. So similarly, you would also have the menu where you can go to the next STS, the start of data stream, or any TLP, or if you are analyzing from the upstream, you would like to go to the next downstream packet. So similarly, you have many features on the software menu. You even have a feature to set unlimited number of markers. You can set unlimited markers on the result screen, then use the go to marker feature to go to any marker Then if you would like to go to any particular index, you can just select the move to index and go to that particular index. Then if you would like to go to the next TLP, just click on the next TLP and it will go to the first occurrence of the TLP. So these are the various features that are available in the software on the result screen. The next thing is, on any given packet type, you can have the option to add additional columns. So whenever the packet type is selected on the software UI, it automatically gives the various column options where you can choose to highlight any of these options. Next, these are the frame views where the frame of all the packets are displayed as per the specification. On the right side are the LTSSM view. As I told you, it updates in real time with the LTSM substates. You even have the feature to link from the LTSM view, that's the substate view, to the result view by just clicking, and it automatically takes from the LTSM view to the main view. Okay, next, coming to the other features. Sorry, I'm going a little faster due to the shortage of time. So we have other very powerful search and filter options. So you have both the search, then the filter in, and also the filter out options. So in the filter in options, you have multiple levels of filter in, where you can filter in multiple packets along with the packet types. Example I will take is a filter in packet of any lane rate on both sides, a packet type of any TLP, and along with it, a DLLP for its acknowledgement DLLP. So I just make the selection. So it's a simple filter and then click on the filter. So you will have the filtering here, where it will show the filtering of the data, and the updated results will be shown on the filter view. So as you can see here, you can see the TLP along with the DLLP, the acknowledgement has been shown on the filtered view. Next, coming to the NVMe view, we have a separate NVMe view which shows all the NVMe commands analyzed by the protocol analyzer. So you can see the various NVMe commands along with some of the write transactions, 4 KB write transactions, and admin. You see both the IO commands as well as the admin commands. The admin commands are marked separately with a A tag. You have the timestamp and also the start address of the NVMe command along with the end time. You can just click on the NVMe command here to show to the start of the NVMe command this, and also expand it to show the details of the NVMe command of how it is present. Next, we even have the configuration register details, where all the register details in the capture are automatically displayed. You can select any register and then click on that particular sub property to see the property details. So all the registers that are available in the PCIe 4 KB space are automatically captured and the values are displayed here. So even the protocol analyzer supports the capture of low power state. So whenever if the low power state enable has been acquired in the register, the same can be captured in the PCIe protocol analyzer. So this is in short about all the software. We even do provide some of the analytics features where you can show the total count, and also in case of any LCRC errors, even if there are any LCRC errors or the frame sequence error for the TLP, the count is shown. Along with it, it automatically you can search by clicking on the count, automatically goes to search. Okay, I'll stop the software exercise and we will take the Q&A due to shortage of time.
Thank you, Pradesh and Vibha. So we'll move on to the Q&A section. Some of your questions have already been answered in the Q&A session itself. Okay. The first question is, what is the storage capacity of the protocol analyzer?
Yeah, I'll take up this question. So we support 16 GB by default, and it can be extended up to 64 GB with additional license. And for Gen 5, we have even support up to 128 GB.
The next question is, what are the types of interfaces supported?
Yeah, I think I have already covered it in the session. So we support as of now M.2, U.2, CEM, SD Express, and E1.S, and we are developing the other interposers like E3.S and all. So we'll be supporting all interposers shortly.
The next question is, can we link from LTSSM states to the main result?
Yeah, sorry. Yeah, Vibha.
Yes, as I have shown during the demo, we can link from the any LTSS, even from the substate to the main result by just clicking on the substate, and it will go to the where the transaction has happened on the main screen.
The next question is, can the same hardware be used for Gen 3, 4, or 5?
Yes, so we support up to Gen 5 with the same hardware. So you can initially buy Gen 3 or Gen 4 and later upgrade to Gen 5.
So, thank you all for joining us today. You can visit our website at www.prodigytechno.com to see our full range of protocol analysis solutions. You can also always write to us at contact@prodigytechno.com. Thank you all for joining our webinar today.